In this video, we're going to review what work problems are and how to set up work problems. Primarily, we're going to focus on lifting liquids out of containers. It could be a swimming pool, it could be a water tank, it could be a tanker truck, it could be a container underground, it could be a water trough. So we're basically going to be looking at how much work is required to lift liquid out of some kind of container. Before we do that, let's review briefly what work is and what force is. So work is basically a force applied through a distance. That means that if I'm pressing on the table as hard as I can, but the table doesn't move, then I have not done any work. To do work, the object you're applying the force to has to actually move. So in the formula, work is equal to force times distance. In symbols, this becomes work equals force times distance. Now let's talk about what force is. Force is the mass of an object times its acceleration. Remember that mass is not weight. Weight in pounds is a reflection of the gravitational force on the mass of your body. Mass is literally the number of atoms and particles that make up you. And that would be the same amount whether you're here, on the moon, or out floating in space. Weight depends upon a gravitational force, so your weight is not the same here on Earth as it is on the moon or out floating in space. In symbols, force is equal to mass times acceleration. Now, if we're going to consider some kind of tank, and let's say we have an inverted conical tank like this, and we have water in the tank, and I'm trying to lift the water out of the tank, so I've got this sort of floating pipe where the water is coming out of the pipe at the top of the tank. The force that is applied to the water is gravity. So in this case, our acceleration is gravity. So gravity in the metric system is 9.81 meters per second squared. And that's the unit that we're going to use so that we can get more significant digits. Sometimes 9.8 is used, but that's only 2 significant digits, which is frankly not very much. So we're going to use 9.81. The next thing we need to consider is the mass of the liquid we're trying to lift. So in this case, if we're thinking about mass, how are we going to measure the number of particles, the number of atoms that make up all the liquid in the container? In that case, what we need to do is we need to think about the liquid as being a more or less uniform substance. In other words, all the way through the liquid, at every part, the liquid is exactly the same. In other words, it needs to be a well-mixed liquid. That means that we can't have more sediment in the liquid at the bottom than we have at the top. If that's the case, then the density of the liquid should be uniform. Density is a measure of the number of particles in a particular substance per unit measure. Now, density is not always per unit volume or per square unit or per unit of length. It depends on the object you're looking at. When we lift liquids, we're lifting a three-dimensional object, so our density will be three-dimensional as well. So when we're looking at mass, what we'll have is the density times the volume. Since we have density times volume to represent the mass, we need letters to represent these in the formula. We use the Greek letter rho, which looks like a P, but is in fact an R in the Greek alphabet. And we use an uppercase print V for volume. So rho times V gives us the mass of the liquid we're trying to lift. This will replace the M in the force equation. The A in the force equation will be replaced by our gravity, 9.81 meters per second squared. If we put this together into the work formula, we'll have the following. We now have work is force applied through a distance. Force is mass times acceleration. Acceleration when you're lifting is actually a reflection of the gravitational force, G. So we have mass times gravity times distance. Mass is measured by the density of the object times, in this case, its volume, since it's three-dimensional. So we have rho v g d. This is the formula we'll use to compute work. This formula will basically not change. Since the density of the liquid will be considered to be constant and gravity is a constant, you may want to leave these as letters until you are finished with your calculations. Then you can plug in 9.81 for gravity and the particular density for that liquid. In other words, you may want to write the formula as rho g times v, then d. Let's return to the picture we have here. We're going to lift the liquid out of the tank with some floating pipe that stays on the top of the water. We're going to do for the lifting liquids problems what we've done for the area problems and the volume of revolution problems and arc length. We're going to divide this into tiny little pieces and add all the pieces up. In other words, we're going to take the limit of a Riemann sum, which will give us a definite integral. To do that, we need to slice up the water. If we're going to slice up the water, we typically will choose an origin. The origin natural places would be at the top of the tank or at the bottom of the tank. If you put it at the top of the tank, realize that all the values below it will be negative. If you put it at the bottom of the tank, then everything above it will be positive. It's my choice to typically put the origin at the bottom of the tank so that I don't have to deal with negative y values. Let's draw a larger picture so we can show what the slices will look like. Here is what the graph looks like when you make it larger. You'll see that I've placed the y-axis coming down through the center of this cone-shaped tank and going through the point at the bottom. The point at the bottom is the origin, so all of these represent positive y values. The water level is here, but the height of the tank is here. Notice they are not the same height. I've sliced the water into tiny little slivers that are very, very thin. I'm going to do this so that I can create a Riemann sum. And you'll see I have another layer of water down here. Now, the tank has a pipe that's going to come down as the water goes down, and it's going to lift the water from where it is, pump it up to the top of the tank, and directly out. If I'm going to do that, knowing that work is force applied through distance, it should be more work to have to move a layer of water that's at the bottom than a layer of water that's at the top because of the distance involved. However, in this case, my layers are not the same size. As I go down in the cone-shaped tank, the water layers become smaller. From a cross-section view, the water layers look like rectangles or strips, like we used in the volumes of revolution. However, if you're looking at them from above, they are in fact coins again. These are discs because the tank itself is a right circular cone. So in this case, what we need to do is compute the work required to move the water out of the tank. In order to do that, we need to know a couple of things. We need to know what the radius of the original tank is, and we need to know what the water depth is, and we need to know what the height of the tank is so that we know how far the water layers have to move. Let's put some numbers on our example so we can start computing. I have set the height of the tank to be 15 meters and the original depth of the water to be 10 meters. The radius of the tank is also 10 meters. Now the problem for us is that the radius of each layer of water is not 10 meters, nor is the depth of each water layer going to be the original depth of the water in the tank. We need to compute what the radius of each water layer is and also what the depth of the water layer is. The easier part is to compute the depth of each water layer first. Since this is my y-axis here coming up through the center, then the depth of each water layer is basically just the y value. So the depth of this water layer is its y value, and the depth of this water layer is also its y value. That pretty much takes care of the depth of each water layer. Now the problem for us is, what's the radius of the water layer? Since this is a conical tank, you can see that it is getting smaller as it goes down. The trick to setting up a conical problem is to realize that you have similar triangles. So let me label the radius of the water layer here by putting this as R, say, we'll call that one R1, and the radius of that water layer as R2. Now, how can I relate R1, R2 with the radius of the tank and the height of the tank and the depth of that particular water layer? If we look at the picture, do you see that I can actually draw some right triangles, and this represents the original tank, where the depth of the original tank is 15 meters, the radius of the original tank is 10 meters, and this angle right here has to be a right triangle because it is a right circular cone. Once I have that, can you see the other right triangles formed by the other two water layers? There's the right triangle for R1, and here's a smaller right triangle for R2. Let me put these on the triangle so you can see them. So here I have R1, and down lower somewhere I have R2. But because these radii are parallel to the radius up here, that means these angles are also right angles. If these are right angles, then that means that the triangle that's formed by the large tank, which I've outlined here in red, has to be similar, not equal, not congruent, but similar to the triangle I'm going to outline here in green. That would be the one for R1, and it's also similar to the triangle for R2. Those are similar triangles. Similar triangles do not have equal sides, but they do have proportional sides. Once I know that, I can write the following proportion. The radius of the tank compared to the height of the tank has to be proportional to the radius of the water slice divided by the height of the water slice. So in words, what we've set up is a proportion. Radius of the tank compared to the height of the tank has to be the same proportion, reduced as a fraction, as the radius of the water slice to the height of the water slice. Now the height of the water slice is the y value, which is here. So we're going to set up this proportion and plug in our values. The radius of the tank is a constant. It's always 10 meters. It never changes. The height of the tank is a constant. It's always 15 meters. It never changes. The radius of the water slice does change as the water level drops in the tank and goes down. So I'm going to leave that as a variable r. Now what about the height of the water? The height of the water in the tank also drops as the water level drops, so I'm going to leave that as y. Now notice that the meters and the meters on the left side cancel, and so I have only a fraction on the left, and I can reduce 10 over 15 and write that r divided by y has to equal 2/3. That means the relationship between the radius of every water slice to its height has to be 2/3. This will let us complete the problem. Let's look at the next piece. Now you may be wondering why we have to go to all this trouble to compute the work. Why don't we simply find the volume of all the water and compute its mass and then multiply by gravity? The problem is Because it has to move a different distance, and because the mass is different at each level, the force is not constant. Although gravity is constant, the mass at each water layer is not constant, so it's changing. This is an ideal situation in which to apply calculus. So what we need to do now is set up the work formula into a definite integral. Let's look at the form that the definite integral takes in words. In words, the integral is going to go from the lowest height of the liquid layers to the highest height of the liquid layers. Be very careful here. The limits of integration refer to the levels of water. They do not refer to the height of the tank. They refer only to the liquid being moved. In our situation, our lowest water level is going to be at y equals 0 because I set the origin at the bottom of the tank, and there is water at the bottom of the tank. So mine is going to start at y equals 0, and my highest layer of water I have to move is up where the water reaches. The water does not go to the top of the tank. I can't move water I don't have. So my highest water layer has to be at the original depth of the water, which is 10 meters. So mine is going to go from 0 meters to 10 meters. And you'll notice that I've included the units to help me determine later whether or not I've worked it correctly. The next thing is we're going to use our formula from over here for work, and we're going to put it into the definite integral. I need to multiply by the density of the liquid by the volume of the liquid layer, not all the volume, just the particular extremely thin slice of water I'm lifting up. Then I multiply by gravity. Then I multiply by the distance that particular layer of liquid moves. Now, in order to do that, let's think about what these are going to be. In my case, I'm moving water. Water has a density of 1,000 kilograms per cubic meter. It is a constant. It will never change. So because it will never change, I'm going to leave it as rho until I am done with the rest of my calculations, and in the very last step, I'll plug it in. The volume of each layer of liquid changes from the bottom to the top. These little coin-shaped pieces become smaller as I go down or larger as I go up. The volume's not constant, so I'm going to have to put in some kind of expression for it. The next one is gravity. Gravity is always a constant on Earth, roughly, so it's 9.81 meters per second squared. We can leave it then as g, just like for the density rho, and we can plug that in as the very last step. That means we need to deal with the volume and the distance moved. You'll notice that in my integral up here, in words, I do not have a differential. That is not accidental. I did not forget the differential. The differential is actually hidden and already included in the volume. Let's talk about the volume. Coming back to the original picture, I've put in the corner what it looks like to have a single layer of water. The cross-section view, viewed from the side, makes it look like a strip. The bird's eye view, looking down from above the tank, makes it look like a circle because the tank itself is a right circular cone. If I want to find the volume of this single layer of water, I need to multiply the area of the base times the height of that particular layer. The height of the layer is the differential. The differential here is going to be dy. This tiny little measure there, just like it was when we did volumes of revolution, that is the differential dy. To find the area, I need to take the radius of the particular water layer and square it and multiply by pi. So the volume for this particular layer of water has to be pi r squared dy. every layer of water has the same volume formula. The dy's will be the same, but the radii will change. As I come down in the tank, the radius of each layer of water gets smaller and smaller, but the formula doesn't change. Area of the base, pi r squared, times the height of the three-dimensional shape, which is the differential dy. Let's put this in our formula now. To put the volume in, I need to include pi times the radius squared, and I have the differential dy. We always put the dy at the back, which means that our volume is actually in two separate pieces in the integral. Since everything is multiplied, this is not a problem. Remember that multiplication is both commutative and associative. I can reorder any way I like. Now that I've dealt with the volume, the only thing left is this distance. What distance does each particular layer of liquid move? Let's look back at our picture. Looking at the picture, my pipe to exit the tank is at the height of the tank. So it is 15 meters directly above the origin. It will float down as the water layers float down. Now, if this is 15 meters from the top of the tank to the bottom of the tank, so this is 15, and this amount here is y, then this layer has to move what's left, 15 meters minus the y value. What about this layer of water here? Again, this is 15. The height of that particular water layer is y, and it needs to move the remaining amount, which is again 15 minus y. Make sure you do not get this set up backwards, or you will get a negative amount of work. So in this case, 15 meters is the larger distance, and we need to subtract the height of the particular water layer. Each water layer moves 15 meters minus its original height. That's how far it moves to get out of the tank. We now have every piece we need, except we still have a problem. What's the problem? If you look at the differential, it's dy. Check the limits of integration. This is y equals 0 to y equal 10. That's not a problem. Rho and g are constants. They do not depend on y. I can take them out of the integral. That's not a problem. Pi is a constant. Not a problem. 15 meters is a constant. Not a problem. Y is a variable, but it is the same as the differential. Not a problem. What's the problem? The problem is r. R is a variable. The radius of each water layer gets smaller as it moves down. It changes, but it is not the variable in the differential, which is y. We have to rewrite r in terms of y and do a substitution. On the first page, remember the similar triangle we set up that gave us a relationship between r and y. The ratio of r to y is 2/3. If the ratio of r to y is 2/3, then r has to be equal to 2y divided by 3. If r is 2y divided by 3, I can substitute that value into the integral and replace r with something only in terms of y. Let's do that now. After replacing the radius, I now have an integrand all in terms of y, so I can integrate. Let's complete the problem by squaring the radius expression, multiplying it out, and then integrating. So first thing I'm going to do, notice I have the rho constant density, g constant gravity, and pi a constant, all on the outside. My limits of integration are y values representing the depth of the water to be moved. I'm going to square the 2y over 3 to get 4y squared divided by 9. Now I'm going to multiply that by the 15 minus y dy. If I multiply out the integrand, that would give me 60y squared meters. Notice I kept the unit of meters from the 15 meters on here. And remember that the expression for r does not have units on it because the meters here canceled. So I have 60y squared meters divided by 9 minus 4/9 y cubed, all in the integrand with dy, integral from 0 meters to 10 meters with the constant rho g pi on the front. Now I can integrate each one using the power rule. So this will give me rho g pi, and this will give me a 60 divided by 9 y cubed divided by 3 with a meter unit attached minus 4/9 y to the 4th divided by 4 and evaluated between 0 meters and 10 meters. In the next step, you'll see that I've reduced the 60 divided by 3, and that gave me 20 over 9 y cubed meters. And I reduced the 4 divided by 4, and that gave me the minus 1/9 y to the 4th. When I plug in my values, I get these two expressions. The second one will all go to 0 since I'm plugging in 0 for each. And what will we get for the next one? Be very careful with the units and watch what happens. When I multiply out the powers, I get 20 meters divided by 9 times 1,000 cubic meters, which gives me 20,000 meters to the 4th divided by 9. Notice that on the second term, I also get meters to the 4th. These meter units should match. When I have meters to the 4th minus meters to the 4th, and I have a common denominator of 9, I can combine them to get a result of 10,000 meters to the 4th divided by 9. Now, meters to the 4th is not the units for work, but we have not included rho, the density of water, and g, gravity on Earth. When we include these units, we will know whether or not we've set it up correctly if we get the right units for work. Work, again, is measured in Newton meters, also called joules. Let's take a look and plug in the density and gravity values now. Let's look at the units. The constant value for the density of water in the metric system is 1,000 kilograms per cubic meter. Very easy to remember, but you don't need to. I'll give it to you on an exam. The value for gravity in the metric system that we're going to use is 9.81 meters per second squared. You can use S squared instead of SEC if you prefer. It's just my habit to use SEC for seconds. Pi is still here. And then we have the 10,000 meters to the 4th divided by 9. If I have meters cubed in the denominator and meters to the 4th in the numerator, then that means that I can cancel all of the meters in the denominator and it will leave behind 1 meter on that particular factor in the numerator. Let's see what the units then come out to be. I will still have a kilogram since there are no kilograms in the denominator to cancel. I still have a meter times another meter on top. That's 2 meters or meters squared. The denominator, the only unit I have left, is seconds squared. Now keep in mind that a Newton, the measure of force, is a kilogram times a meter per second squared. That is the Newton with the capital letter N in print. That's a Newton. This is a measure of force. However, to get it to match this unit, I have to multiply by another meter That's the measure for distance. If you will remember our original formula, work is force applied through a distance. So I have a measure of force, a Newton, times a measure of distance, a meter. This must represent a joule. A joule is the measure of work. So this is the same as a joule, which is abbreviated with a capital print J. Now let's work out the numbers. If I multiply out the numbers, I will end up with, oops, I think I placed my comma in the wrong place. This should be 98,100,000 divided by 9 joules. And since I picked my numbers wisely, I actually can probably do some of the division. I don't know that it's exactly divisible. Let's see. Yeah, well, I can at least reduce by 3. We can try it by 9. I think it'll work. 9 goes into 9 one time with none left over. 9 doesn't go into 8, so I need a 0 for a placeholder. But 9 goes into 81 9 times, and then it doesn't go into the rest. So I should still have placeholders, I think, for these 3, which would give me 10,900,000 joules of work required to lift the water out of this conical tank that is 15 meters deep and 10 meters in radius, with water originally to a depth of 10 meters. Let's change the problem slightly so that we can make sure you understand how to set up the integral. The integration itself on a water lifting problem or a liquid lifting problem is usually quite simple. The setup, on the other hand, can be quite difficult. Let's suppose that we again have a conical tank, and this time the original radius of the tank, we'll make this 8 meters, and we'll make the original height of the tank be, oops, I didn't get quite to the bottom. Let's make this 20 meters. And let's suppose that I don't want to lift all the water out of the tank. Let's suppose I only want to lift some of the water out of the tank. So let's suppose that our original level of the water is at, let's make it 12 meters. So the original depth of the water is 12 meters. And I want you to remove the top 2 meters of water from the tank, but only the top 2 meters. So lift the top 2 meters of water from the tank. How much work does that take? How would we set up this problem? If I'm going to lift the top 2 meters of water from the tank, then I can set up my equation essentially the same way I did before. Remember from before, we need to go from the lowest liquid layer that we're moving to the highest liquid layer we're moving, density, volume of the liquid layer, gravity, and then the distance the layer moves. So in this case, if I'm moving the top 2 meters of water from the tank, then I'm only moving water from a depth of 10 meters up to 12 meters. That's the 2 meters of water I'm moving. So I would set up my integral to move water from 10 meters to 12 meters, again assuming that the origin is at the bottom of the tank. I'm not moving all the water. I'm not moving the bottom layers of water. I'm moving the top 2. The rho and the g will not change. Those are constants. Pi will not change. Does the volume change? If we look at what we did before, notice that the fraction we got was dependent on the ratio of the radius of the original tank divided by the height of the original tank. This is dependent on the particular tank you have. So we need to set up another similar triangle. We have the original radius of 8 with an original depth of 20, And next to it, we can put our smaller radius for the water layer, which is R, and its depth, which is the Y value. And we can set up our ratio into a proportion. So we have radius of the tank in 8 meters divided by height of the original tank, 20 meters, has to be proportional to the radius of every water layer divided by the height of every water layer. Again, to replace R, we need to solve for R, and I can reduce this fraction by dividing both pieces by 4 and canceling the meters units. So this gives me R equals 2 divided by 5 times Y. So my R has changed. It's no longer 2Y over 3. It's now 2Y over 5. So over here, when I write down the volume, I need to remember that my volume is actually composed of two pieces. The area of the layer, which in my case is a circle, so it's pi r squared, and the depth of the layer, which is the differential dy. So I have pi, my radius is 2y divided by 5, quantity squared with the differential, that's the volume, and then I need to know how far is each layer of water going to move. I'm only moving these top little layers from the top 2 meters of water. Now, how far is it moving? If the tank has an exit pipe that is at the top, then it would be 20 minus y. But let's change it a little more, and let's suppose that the height above the tank for the pipe outlet is another 3 meters. If the pipe outlet is 3 meters above the height of the tank, then it's actually 23 meters from the bottom of the tank to the top. So if this is 23 and the water is at height Y, then each water layer has to travel 23 minus Y meters to get out of the tank. So the distance moved will be 23 meters minus Y. Again, this sets up the problem, and from here all you need to do is complete it. And it looks like I accidentally have in too many pi's, so I'm going to remove one of my pi's. I should only have pi once. All right. Hopefully this explains to you how to do this. I'll work another example using a different shape so you can see how a different shape works. But conical tanks are a not uncommon problem to see lifting liquids from.